And we're ready. All right, so this one's not in the notes, but I'm going to have you write something at the end of this that's going to be very helpful to you. And certainly helpful in solving out the Friday bell work. So we want the probability that a particular knee surgery is successful is 0.85. We want to find the probability that 3 knee surgeries are successful. Remember, this is 3 events, right? It's not 3 favorable surgeries that we want. It's 3 events. The first surgery, the second surgery, the third surgery. So we're looking for the probability of success, success, success. All right, I'm going to have some fine person help me. Not that fine person, because they're not here. Anybody at yellow? What's the probability of a successful surgery? Remember that probability can be stated as a fraction. Oops, that wasn't move. A decimal or a percent.
Yeah.
Well, we can't calculate with percent, so we'll put 0.85.
Yeah.
I guess multiply that by 3/3.
No.
After the 3 surgery?
No.
Oh, you do know you do.
So the probability for the first success is 0.85. So this is success, then success, 0.85. That's how you get probabilities that are greater than 1.
Yeah, yeah.
So what would be next? Let's see if these next.
Another 0.85, right?
Another 0.85. There you go.
Oh,
And then
Yeah.
the third success.
One more 0.85.
And one more 0.85. So you multiply by the probability every time the event occurs. All right? So you've got, this is event 1, event 2, event 3. There should be 3 values multiplied. This is a page where we're going to want somebody with a calculator because that's not so fun to do in our heads. So someone could multiply 0.85 times 0.85 times 0.85 or 0.85 cubed.
0.614125.
Oops. I have to write it down here. 0.6414125.
614. Yes.
Okay. I'll just put it down there. It doesn't fit. All right, so that would be the probability of 3 successes in a row. So what about the probability that none of the 3 surgeries is successful? So now we want the probability of failure, then failure, then failure. Hey, where's my letter? The board makes me think I'm losing my mind. Like I didn't write a P up there. And I swore I wrote a P. And it's coming up now. Now. And usually I get fed up. And I write the P again. And I've got like 6 P's over itself. Let's try it again. So hopefully this will come up. There it goes. Failure. I told you. And we're waiting for the rest of the word. One of those failures looks like failure. That's what happens when I can't see the word when I'm writing. All right, come on. Oh, I'm holding the eraser. Never mind. It's going to start erasing it. All right, so probability, failure, failure, failure. Maybe we'll fix this word so it doesn't look like failure. All right, so now we looked at probability of success. Is there anything between success and failure? No, you can't kind of be successful. I mean, either it's successful or it isn't, right?
So you just do the same and divide, right?
No. So now you got to figure out what's the probability for failure. So if you get the first part right, you'll probably get the next 2. Orange 4.
Oh.
So what's the probability of failure? So what's the probability of one failure? Just one failure. 0.15. You're putting in an extra digit there, right? Because success plus failure, right, has to equal 1. Right? So if we take 1 minus 0.85, that's going to give us the probability of failure. Right? So we have 0.15, then what's going to be the probability of the next failure? 0.15. Right? One surgery doesn't affect the next surgery, right? Just because one surgery is not successful doesn't mean the next person's surgery is not successful. These are independent events. And then, I'll probably write that up on top of the page here. And then how about the third surgery?
0.15.
Yeah, 0.15. Right? So these are independent events. Whoops, a little sideways there. One surgery does not affect the next. All right, so we just multiply the individual probabilities. There, you can kind of see that one. All right, so someone with a calculator, if you could multiply out 0.15 times 0.15 times 0.15. 0.003375. Okay. All right, so this is the part I'm going to, this part I'm not going to have you put your notes, but the part that comes right after it. Because we're going to figure out the probability that none of the 3 surgeries, excuse me, not none, at least one, so I already did none, at least one of the 3 surgeries is successful. Now, you can do this the easy way or the hard way. Now, it's not as hard because there's only 3 things here. But what if there were 30 things, now? Or, for instance, 5, like your bell work. Right? It gets a little more tedious because you'd have to find the probability that 1 was successful, then the probability that 2 was successful, and the probability that all 3 were successful, and add those together. But would you like an easier way that you can use? And the answer is yes. We'd like an easier way. So this is the part you're going to put in your notes. All right, this is called the complement. Wherever there's space from where we left off, or wherever you think it would be most useful. All right, so this is, we saw complement in the addition rule, but now we're going to look at, complement in relation to compound probability. Complement. All right, and you're going to use this. This is a good idea anytime the question reads at least 1. Oops. So, what's the alternative to at least 1? What's the only thing that could not be included in at least 1? None, right? So together, at least 1 plus none equals 1. Because none is the only other option that's not included in at least 1, right? Because that could be 1, that could be 2, that could be 3. The only thing it doesn't include is 0. So anytime you have at least 1, what you can do is take 1 minus the probability of none. And that's a lot easier. It's a lot easier to take 1 minus 0.003375 than it is to find, here was the probability of 3 successes, so I'd have to add 0.614125. I'd have to find 2 successes, which would be 0.15 times 0.85 times 0.85, and add that one together. And then I'd have to find 1 success, which would be 0.15, 0.15, 0.85, and add all 3 of those together. Instead, I can just do this. 1 minus the probability of none, in this particular case, is 1 minus 0.003375, which is, somebody in the calculator? 996625. 996625. So I think you should feel pretty good about your odds here. Over a 99% chance, if there's 3 surgery, at least one would be successful. You just got to be the one. Yeah.
Where did you get the 0.003375?
Oh, from the probability of 3 failures.
Oh, okay.
Yeah. So now that's a hint to your Belver question, which is over here. So 5 multiple choice questions, each with 4 possible answers. What's the probability if you just guess you get at least one of the questions right? So the alternative to getting at least one right is getting none of them right. If you take 1 minus the probability of getting none right, you'll have your answer. So just a little hint there. I saw some crazy, crazy answers this morning. Answers that should have like scratched your head and go, huh? The interesting thing is that it's not a bad probability that you'll get at least one right. And yet there are sometimes that people defy the odds and they manage to get all of them wrong. Did everyone get the part that's for their notes in the notes? Okay. Yeah.
So let's say 1 minus P9 equals 1 minus.
Yeah, it's not that important if you put that one in there because it only relates to this particular problem. But make sure you put the 1 minus probability of none.
So we're complimenting where it says anytime,
It's a good choice. And you can also put this in your notes. All right, so it says complement anytime the question reads at least 1. Maybe quotation marks. Yeah. Because by golly, if you got like 10 events, man, is that a tedious problem. You'd have to find the probability of doing something once and twice and 3 times and 4 times, and all the way up to 10 times. Whereas you can just find 10 failures, which is just multiply something 10 times and subtract from 1 and be done. And so complement just means that that event plus some other event equals 1. Right? So it's everything else but the event. So everything but at least 1 is none. Everybody good? So we're going to look at conditional probability. This can be tricky, but once you get the hang of it, it all follows the same formula, same probability formula. So it's actually not too tricky. This is one we did earlier. I'm just going to breeze through it. We did that before the benchmark. If you have a computer open. Actually, you're okay. So here, for instance, we saw this one earlier. You have a 70% chance of passing the final. You have a 65% chance of passing the class and the final. Find the probability of passing the class given you pass the final. Anytime you see something, the probability of this given that is the conditional probability formula. So if you have 2 events and you're looking for the probability of 1 given the second, that is, I don't know why it says COMB. It's supposed to be COND. I don't know what comb is, but conditional probability. Right? And that's this formula right here. And so the conditional probability formula, the probability of something given something else, probability of B given A, is going to be the probability of both, probability of A and B, and remember you'd multiply those two probabilities, divided by the probability of the given, divided by the probability of A. Right? So we're going to do a couple of them that we didn't do before benchmarks together. That one was in your notes, and we had done that one. If you do need me to slow down because maybe you were absent or something, I can do that. Unless, of course, you're watching this as a recording, and then, well, you can hit the pause button and slow me down. And so we did this one in class already, the second one here. And so we're going to do, we did this one in class very quickly. Just a reminder, formula for conditional probability. So probability of A, given that B has already occurred. So that A slash B or something slash something else, it means the probability of this given this has already occurred. So you're limiting your choices to just the times when B has occurred. Right? So notice that it's actually more likely. So it's the joint probability divided, I should actually point to it. It's the joint probability, which is right here, divided by the probability of the given, which is right here. Right? So you're only looking at those times. You're not looking at any other time. And I think the next one, if it's a question about this one we did already. So I wanted to at least look at it a little bit before you took the benchmark. That was probably the most new. So this is the one we're up to. And this one is in your notes. And actually, maybe before we do this one, let's do this one just to review this formula. And then we'll come back and do the Venn diagram. And then I have another Venn diagram, which is actually a little bit trickier. Yeah, so let's say this one first. It's an easy problem, and then we'll go do the Venn diagram, and then we'll do just a tiny bit trickier problem. So we want the probability a student is a junior. So the probability that a student is a junior and in Algebra 2 is 40%. I just made those numbers up. So the probability that some student is a junior and in Algebra 2 is 40%. There's a lot of juniors that year, and they're all in Algebra 2. Or a lot of them are in Algebra 2. What's that?
It'd be fun to find these things.
Yeah, it would be, and actually have not make up the numbers. The probability that a student is a junior is 60%. Find the probability that a student is in Algebra 2 given that they are a junior. Okay. So in this question here, it's going to be the probability of A given B. In this case, actually, let's write it so it matches the question here. The probability of Algebra 2. This one's not. The probability of Algebra 2 given junior is equal to the probability of Algebra 2 and junior, so that intersection. That's supposed to say junior. That's good enough. Divided by the probability of junior. All right, so what should I plug in for the probability of Algebra 2 and junior? Oh, wait, no, that one's good. Red 3.
Do you want it in decimal?
Yes.
0.4? Over 0.6?
Yep. And then that would just reduce to 4, 6. We move the decimal point over, divide, multiply it by 10, and then divide by 2. Oops. Divide by 2 to give you 3/5. Right? And that's really all there is to the problem. It's just recognizing that we are limiting ourselves to just the times where the given has occurred, right? And so we would use the conditional probability formula.
Would it reduce to 2/3?
What did I do? Oh my gosh. Where did I come up with 3/5? Now you're all really confused. I have no idea where that came up from. Yes, it would reduce to 2/3. think 3/5 is an answer coming up. Let's see if 3/5 is an answer coming up. All right, let's go back to that and the Venn diagram here. And we're going to fill it in first. And then we can answer all the different probability questions. All right, so, whoops. Except, don't look at it. Oh, now I got to change the numbers. I forgot to erase that part. Ah.
But it's filled in with notes.
Oh, is it? Oh, no, then that's no fun. I forgot I had done that. Oh, no wonder they all got it right first period. It's filled in your notes. All right, I'll just put it back. All right, so it was 4 was out here. All right, so neither, when you're filling these in, I want to do it together. That's okay. We'll have one we can do together. A little later on in this lesson. Oh, look at that. I'd keep hitting undo, but it would take too long. So when you're filling these in, always find the intersection first. All right? Both. All right? Fill that in first because that will help you determine the rest. I know sometimes your neither is easy to figure out and sometimes it's not. Sometimes you just have to wait till you get everybody else and you realize, okay, there's supposed to be 40, I'm missing 4 students. And they must be outside here. But this time they told us there were 4 outside. So 16 students play football. So if 5 play both, they're already counted for. There's 11 more students. They just play football. And if 5 students play basketball, already listed there, and we want,
It says 16 students play football.
there's the 16, 11 plus 5. Oh, it doesn't tell us how many play basketball, but that's okay, right? Because we know how many play neither, right? And this has to add up to 40, right? So we've already got 19, so there needs to be, it has to add up to, so there has to be 21. Right? Did I miss anybody?
No.
Wait. How did I get?
11.
Oh, 20. It needs to be 20.
16.
It needs to be 20. I decided to see 11 as a 10. The sad thing is that I did this earlier today because it was not filled in on mine. I know. Well, that'll fix itself. There we go. And now we'll fix it. Okay, let's find the probabilities. All right, so we want the probability of football. What would that be? Orange 1. Out of? Yep. And so we could reduce that to 2/5. No. Not unless it says, so if it was just football, I'll write it over here. So just football would be, I have to move the 4 though. We'll just put it here. Would be the probability of football pretend there's a B there. There we go. Probability of football and the intersection of not basketball. All right, so it would have to not include. If it was just football, it would be this one. All right, so it would not include the other part. You don't have to write that part in your notes, but probability of basketball, orange 5. Yep. And that's going to reduce to, yep. Probability of football and basketball. Anybody at orange? Yep. How about the probability of football or basketball? No, 4 or yellow 3.
Football and basketball. I think 36 over 40.
Mm-hmm. Yep. So here we would add the probability of the both, right, the intersection, and then each of the football, not basketball, and basketball, not football. Or we could just simply, we could also, I mean, here we can just count. But if this wasn't, if we didn't have a Venn diagram here, we could also just take the probability of football and that would be combined with the probability of basketball. And then we'd subtract the probability of football and basketball. So that's the other way if this were not a Venn diagram. All right, so here this would be 36 out of 40, which is 9/10. How about the probability of football given basketball? Luis. So as a reminder, it's going to be the probability of football and basketball divided by the probability of basketball.
Would be 1 over 5?
So what's the probability of football? Let's calculate it all out so everyone can see it. So it won't be a mystery to those watching. So what's the probability of football and basketball?
5.
5 over
40.
40. And then we would divide that. So I'm going to move that one down a little bit. Hang on. The other 0 will be coming. This is exceptionally slow today. Stop. Just move it down. Yeah, let's see if I come over here. Oh, nice idea, but I can't find the cursor. Oh well, we'll. Holy cow. It just doesn't want to be there. Oh, well, I'll just rewrite it. Simple. I know. Is it there? There we go. All right, and then we'll divide by the probability of basketball. So what's the probability of basketball?
20? 25.
25. So that would be 25 over 40, right? So that would be the same as 5/40 times 40 over 25, right? So multiplying, dividing by a fraction, same as multiplying by the reciprocal. The 40s would cancel, and the 5 and 25 would reduce to 1/5, right? So your answer was right, but we want to make sure everyone knows how to solve it. How about the probability of basketball given football? Right? So now, as a reminder, be the probability of football and basketball divided by the probability of football. And hopefully I have enough space to squeeze that in. A yellow 4.
Football 16 over 40.
So what's the probability of football and basketball?
Football and basketball is 5.
Over?
5 over 40.
Uh-huh. And then probability of just football?
Football is 16 over 40.
Right, so that would be 5 over 40 times 40 over 16. The 40s will cancel 5 over 16. Right? So that's how those are done. Any questions on these ones?
It's 5 over 16.
Oops, yeah. Somehow the, I don't see the 6. And do we see the 6 now? No. Well, that's a 5 over 16. An exceptionally slow computer today. I'll fix that afterwards. Everybody got this one? All right. So let's do another problem. It's a little bit different. It is a conditional probability formula. Let's see if it'll change the page, given that it didn't want to write the 6. Oh, it had no problem changing the page. It just didn't want to write the 6. All right, so we have the probability of a dog that is white and a poodle winning the dog show is 0.45. The probability of a dog being white, given that it is a poodle, is 0.6. What's the probability of a poodle winning the dog show? Now we see the key word there, given. By the way, it was immaterial that the dog was in a dog show. That was just extra stuff. But we see the words given, and we see white and poodle. Right? So remember the setup. Right? So it's going to be the probability of A given B is equal to the probability of A and B divided by the probability of B. All right, so probability of A and B means, A given B means the probability, so we're looking here for probability of a poodle. Right? So we're looking for the probability of poodle given, or at least that's the answer to this question, this particular probability. Looking for the probability of poodle given white. All right, so that would be equal to the probability of poodle in white divided by the probability of white. All right, so let's see if we can figure out where these numbers go and what we're actually solving for. Where should the 0.45 go? Where should that value go? What's it going to replace? Yellow 5. Where should the 0.45 go? So the probability of a dog that is white and a poodle winning the dog show is 0.45. So I can do this. I can do A, B, and C. So would it go here, A? Would it go here, B? Would it go here, C? B is correct. All right, so this is going to be 0.45. We just changed it from 45% to 4.5%. 0.45. How about the 0.6? Probability of a dog being white, given that it is a poodle, is 0.6. Where should I put that? So we filled up B. A or C? Nobody good there. How about anybody at red?
A.
You are correct. It goes here. All right, so this is our conditional probability was 0.6. What we're actually looking for was the probability of being white. All right, so we're looking for probability of white. So we can solve this by multiplying both sides by the probability of being white. Right, we got to get that out of the denominator. So we'll multiply both sides by probability of white. I'm going to try to get both classes up to the same spot. I think the next class is on the next page. So these would cancel, right? And I'd have 0.6 probability of white equals 0.45. And then we just divide both sides by 0.6. And that's how this one is solved. So if someone can divide, oh, actually I don't need you to divide, never mind. 45 over 60, right? We can multiply by 100, and that does reduce to 3 over 5. Wait. 3 over 4. 3 over 4. And there we go. So the probability that the dog would be white, given that the probability the dog was white was 3/4. All right, so you can solve for any one of these. One of the bell works was like this. Now you can put that anywhere and isolate either variable. Any questions on this one? This one was just a little trickier. It's really similar to a benchmark question. I think the next question is a table question. What's that? The next question should be yay. All right, so we're gonna finish up this question, and this one can be tricky, only because you have to figure out what they're really asking for. I'm gonna move this up a little bit. Before we get started, I need a bunch of people with calculators, and we want to add all the columns and all the rows, all right, to make it a little easier for ourselves. All right, so actually if we can get 2 people to add the columns, I can do some of the rows. This one of these I know is really, really easy. I think it was, this one was easy. It was, say I got 8, I got a 2, I got an 8, I got a 6. Okay, I took care of that row. So if somebody could add 1537 plus 2808. Yeah, add that one across.
45,
What's that?
43, 45.
43, 45. Can you add 2410 and 2951? While they're doing that, can somebody add the 2 columns?
The first column.
Okay, what's that?
11655.
And actually remember the second column. It was 11656. Can you just add both of those 2 together? And then we just need the other 2 rows.
The last row is not the Midwest one, is 5361.
5361, and then this one is
5320.
and then how about these 2 added together? What was it? 23?
311.
311?
Yeah.
Like that? Oops, sorry, but I wrote a 0. All right, so now this is actually conditional probability in disguise. Is that right? 23,311, right? All right, so we could rewrite that as the probability. So that an immigrant is from the West, we could rewrite that as the probability of West given immigrant. All right, because we're limiting it to just the people that are immigrants. And this just means people leaving a region, people coming into a region. All right, so and this is in your notes, that's going to be equal to the probability of West and immigrant divided by the probability of the given immigrant. Right? So the way this is worded, it's the probability of West given immigrant. All right, so let's find the joint probability. All right, so where would we find, I'll just call it out to the class, where would we find the probability of West and immigrant? Which number would that be?
What is 2654?
2654 is correct. All right, and that would go over the total number of people, right? So 2654 over the whole number of people, which was 11,656. And then, what's that? Oh, excuse me, I got the wrong number of people. This is going to be the last problem we do. Yeah. So I'm running out of space. I'm going to do this up above here, okay? So here's A. So we have, that probability is going to be 2654 over the total number of people. So that would be 23,311. And then we would divide by the probability of immigrant. So what's the probability of being an immigrant? What was the number of immigrants we had?
11,656.
11,656. All right, and then over 23,311. Now notice what's, so now we can calculate it out. So this would be 2654 divided by 23,311 times the reciprocal. So 23,311 over 656, which is equal to 2654 over 11,656. So notice that the total cancels out. So if you remember that when you flip it, you're only going to be left with this and this, because we're only looking at that population. So on the next ones, we're going to skip the whole spiel so we can take a little less time. Actually, I think we could finish. Let's do the probability. So this is that someone selected from the South is an immigrant. All right, so we're only selecting people from the South, so it's the probability of immigrant given South. All right, so we're going to leave out the total, all right, because it's going to cancel anyway. We did it one time. And normally, make sure you do it all the time, but in this particular problem, that total is going to cancel because it's going to flip over. All right, so how about the probability of being an immigrant? So how many, so that would be the probability of immigrant and South. What's that probability? How many people are both an immigrant and from the South?
5042.
Yep. And then divided by the probability of South. And that was 8286, yeah. So technically, it's 5042 over 23,311 divided by 8286 divided by 23,311, but those would cancel, and that would leave us this. We're not going to bother to reduce. The rest one is really, really quick because it's not conditional at all. Notice it doesn't say someone from some area. It just says someone is an immigrant and from the Midwest. So not to be confused with conditional probability, this is just compound probability. Immigrant and from the Midwest. So how many people are both an immigrant and from the Midwest?
2951.
What was it?
2951.
2951. And over our total number of people, 23,311. Oops, with one too many 11s. So I did catch up both classes to the exact same spot. I did post the closings. So there are 4 closings, but they tend to be a little on the short. Actually, there's 3 closings. Monday and Tuesday got 1 closing, and it's a matching, and you just explain. And then, so there was a closing for today, but it is posted. And then before I sign off, so if you're all packed up, you guys are dismissed. For the people watching it, I'm going to fix one number for you. Finally, I can fix that 6. Maybe.
Yeah, Mr. Shike.
Boy, that 6 just doesn't want to be there. Well, know that that's a 6. I've never had a number be so stubborn before. Maybe we can write it someplace else. I give up. That number's a 6. All right? Bye for now. Thanks for watching. I've never had a number not want to be so badly. Thank you.